All right, we're going to go ahead and get started with the pre-cal class because we do have a lot to go over today. Today we're going to be going over chapter 2, which is nonlinear functions. So before we start over our class, let's go over last week's homework, which is graphing and analyzing the transformations on the function f of x is equal to 9 times 3x plus 2 whole squared minus 8, which is a quadratic function, which is in vertex form. So before I go through the answer, would anyone like to share the way they finished, the way they completed the problem, or their answers? You go ahead and share it in the chat, or you can share it in the Q&A window. Anyone got an answer? Did anyone complete the homework? Would anyone like to share the answer they got? If not, then we can go ahead and start going over the answers for this. This was the problem to review. This was a problem from last week, and we're going to go over our transformation rules for functions. So remember, a plus outside of the original function f of x would be a vertical translation. A minus would be a vertical translation down, while the plus inside the f of x, inside the function, would be a left and a minus is right. We have a reflection over the x and y axis depending on outside or inside the function, as well as the location of a constant for a vertical stretch, compression, or a horizontal stretch or compression. Okay. So now let's go ahead and take a look at the answer. So this is classifying transformations. We classify the outside constant as an A, with that one as B. Inside the x the x minus h. That's it. The h would be the translation left or right, and we have the k. So here is what the graph would be for your function. So the new function would be in red, and your parent function, for this one, the parent function is a quadratic function. So we're going to go back once more, and we're going to see if you remove that a is 1, if b is 1, a and b are 1, and h and k are 0, which means, as we remember from your vertex form, for quadratics, if h and k are 0, if your vertex is at 0, 0, and you don't have any stretches or compressions, you would end up with the parent function. And that parent function is just f of x is equal to x squared. So transformations on the parent function in this particular problem would be a vertical stretch by a factor of 9, translation left by 2 by 3 units, a horizontal compression by a factor of 1 by 3, and a translation down by 8 units. Are there any questions about these transformations at all? What the answers were for last week's homework? Are there any questions at all? Please let me know if you do have any questions, because this material is mostly a review, and all stuff you're going to need to know. You're going to need to be very fluent in when we continue on with the course. So if there are no questions on the transformations, that concludes the review of the homework, and we can go ahead and continue on with our new material for this class. So as for an overview for today, the second unit will cover nonlinear functions like power functions, radical functions, polynomial functions, and inequalities. Oh, we're going to go back. Our table of contents has power and radical functions, which is graphing, analyzing, and understanding various power and radical functions, rational functions, which is graphing, analyzing, and understanding those, and polynomial functions, graphing, understanding, and visualizing these polynomial functions, which we'll learn how to get a vague sketch of, as well as inequalities, understanding, analyzing, and understanding what, or solving, or that's supposed to be solving. So we're going to end up solving a couple of nonlinear inequalities. All right, so first off, we have our power and radical functions. If you have any questions at all, please make sure you're asking them. I want to make sure that everybody gets a full understand. Oh, someone asked a question about the homework. Why is it left by 2 by 3 units? All right, let's go back and take a quick look at that. Okay. So let me pull up a let me see if I can pull up a whiteboard. Oh, it's not seeming I can pull up a whiteboard. Okay. Hold on, let me pull up a whiteboard from online. We're gonna go over that in just a second. Think about that as your think about the fact that it is inside the sorry, in this book. Think about the fact that it is inside the parentheses. So you want fill to be. Hold on just 1 minute while I get this. All right. Okay. So now let me pull up. Our problem was f of x what's the trouble with it? Okay. Is equal to 9 times 3x plus 2 whole squared minus 8. All right. Let me go ahead and share the screen. Oh. There we go. Okay, so what we want to do is in our parent function over here, we see that, let me go back a couple slides. Right here, we see that in that, when you're adding that horizontal translation, it's directly on the x. When you're doing a horizontal translation, you do not include that coefficient. So what we're going to have here is, let me move this around one bit. Does not appear that I can switch between slides. Hold on. One quick second, please. Just a little bit of a technical issue. And we can continue. Okay, there we go. So we have these transformation rules, right? And we want that transformation to be only on the x, and we don't want to have that coefficient in the equation, basically. So we have this 9, and that 9 is our vertical stretch by a factor of 9. And so we are only going to take this when we want to figure out our horizontal translation. So we have 3x plus 2 that is inside that parentheses. And from that 3x plus 2, we do not have an expression that only includes an x. We have that pesky little 3 over there that does not allow us to use that 2 as a proper translation on the x. So we're going to take out that 3, and we have x plus. So what happens when we take out that 3 from this 2? So naturally, we're going to divide that 2 by the 3 in order to receive a number that is equal to 2. So we have 2 by 3 times 3 is equal to 2, right? So we're going to put that 2 by 3 right in the middle. So all we're doing right now is we're restructuring this in a way where we can clearly see that this is only an expression with x. So we have that 3 times x plus 2 by 3, and because it would be x minus h, this would be a negative 2 by 3. So a translation left by 2 by 3 units. exponents. All right. So are there any questions on the homework? Any more questions on the homework? All right. Continue on then. So we're going to start with power and radical functions. We're going to start learning about what is a power and radical function, how do we graph them, how do we analyze them, and how do we understand them. So power functions contain a variable at their base and a constant in the exponent, and radical functions contain fractional exponents, or they would contain just a radical in general, just a radical in their in the function, which radical is often a root of some type of like a square root or a cube root or a root to the fourth. So power functions here are characterized by a variable base and a constant power. So here are some examples of a power function. You have f of x is equal to x squared. And you see here that's just a quadratic equation. You have it in black. The quadratic equation looks like a regular parabola. You have g of x is equal to 3x cubed plus 5x. And you can see that's a very stretched out cubic equation. And lastly, you have here this strange looking one, which is 2x power 7 minus 8x power 3 plus 2. And we're going to go over that in the polynomial functions unit, but it still counts as a power function. A variable base and a constant power. Right, so you see none of them have x or y none of them have variable in the exponent, and they always have the variable x as the base of the exponent. All right, so these are what we're going to go over first before we get into any of the complicated stuff is the monomial functions type of these power functions. So monomial functions are in style f of x is equal to kx power n. So f of x is equal to kx power n, where k is the coefficient, x is the variable, and n will be changing. So x will remain the same, and k and n will be changing. So here is a quick way to think about the graphing of these power functions. So if the constant is positive, so if k is greater than 0, you're going to have if k is greater than 0 and you have an even power on that function, so say if it's power 4 or power 2, you're going to have the end behavior shown at the bottom. X extends to negative infinity, f of x extends to infinity, and as x extends to infinity, f of x extends to infinity. And just take a look right there at the end behavior on that one right there. Over here, the end behavior, and as a negative constant, you see a similar pattern. As x extends to negative infinity, f of x extends to negative infinity, and as x extends to infinity, f of x extends to negative infinity. And that's on the even power. Both of them would be facing downwards. In the odd power, you have opposite end behaviors. We also have another representation of these sorts of functions where we have n as a negative integer, even negative integer, and n as an odd negative integer. And this is actually a rational function. We're going to be going over that in part 2. So this is a little bit blurry, but it's a very, very good representation of the type of power functions that you'll be seeing. So the odd and even right here is if the numerator of the fraction in the exponent is odd, then you have quadrant 1 only over an even number. And then odd over odd, you have quadrants 1 and 3, and then you have even over odd, which is called quadrants 1 and 2, which is another way to visualize this sort of graph. We also have our power, which is high number over lower number, or the second one is a lower number over a higher number, and we have a negative power in the third one, which would be a fractional power. We also have this, which is another representation of our power functions with our straight line y equals x, y equals 2x, and y equals x by 2, which is showing us all these various transformations on these functions. So we have, in the second picture, we have our rational functions, 1 by x, 2 by x, and 1 by 2x. And in the last one, we have x power 1, x power 2, and then x power 1 by x power 3, x power 2, and then x power 1 by 3. As for radical functions, so here's a representation of what a radical function looks like. And power functions are radical functions are characterized by a radical in the expression. So here are some examples. We have the ones I'm showing here are square root expressions, but obviously you can have the cube root expressions or the fourth root expressions in here as well. So you have f of x is equal to square root of x plus 2, and g of x is equal to 3 times the square root of x minus 4. So in blue and red. All right. And then you have your radical transformations. So this is similar to the transformations that we have on any, if we go back to the beginning, let's see, transformations. We have this chart right here that shows us that f of x plus d minus c, the c's and the transformations, the translations, the reflections, the stretch and compression over the vertical and horizontal stretches and compressions. And we're going to have a similar thing for our radical functions. Let me see, radical transformations right here. We have a similar thing. So the parent function would be y is equal to the square root of x, but obviously we can have any root in that radical function. We have a vertical translation by k, a horizontal translation by h, and the vertical and horizontal translations, you have h and k. Obviously, remember you have the x minus h, not the x plus h, the x minus h, something very important to remember. As well as you have the reflection of the x-axis, which is y equals negative root x, and the stretch and shrink factors of a. So y is equal to a root x, and the stretch and shrink factors with the a-axis reflection, which is a negative a root x. Keep in mind you can also have that horizontal reflection, but of course then it might transfer into a different shape altogether. Graphing radical. So here for graphing radical functions, what I find is the easiest way to graph a radical function is to make yourself a table, put in x values to the function, and then have a result of f of x values. So you see here, it's just a regular parent function, so square root of x, the x values 1, 4, 0, 1, 4, and 9, and they just plugged it in and graphed it. So we're going to do some of that in just a second. So what I want you to do here is you find 3 x values, put in 3 x values and find their corresponding y values. You don't have to graph it because you can't share the graph. I'm not able to see all your graphs. So find 3 x and y values and put in their coordinates into the chat. And we can go over that in just a second. So all you would have to do here is just generate 3 random x values, plug them in, and come up with a y value. And that's just the basis to graphing these radical functions. Just plug them in and use your result. So we're going to take about 5 minutes to do this. It's 6:21 for me right now. So at about 6:26, we'll reconvene and we'll take a look at all the answers that you've come up with. Feel free to send your answers in the chat or in the Q&A box, or even you can go ahead and raise your hand. Make sure to keep it up for a minute so I can go ahead and allow you to speak. All right, just to make it a little bit more clear for the last one, the only value under the square root is x. For the first one, the only values under the square root are 9x plus 3, second one 2x, and the last one just x. So if that might affect your answer a little bit, remember we've got until 626. I just want you to come up with answers. If you're not able to do all three, pick one and come up with the answer to that one equation. I just need the three x and y values for one of these equations. Three x and y values that will help you graph that equation. For the purposes of this question, it's okay if you decide to estimate the values or if you decide to give an exact value. But just remember that in most advanced math classes, like in any pre-calculus class, any algebra 2 class, you are most likely going to be required to answer in the form of a square root, right? Because sometimes you will not be given a calculator, and it's best to, just put in that exact answer instead of trying to evaluate a square root. So either one is fine for now, but just remember that for most cases, it's best to keep it in exact form rather than estimating. Sometimes for the purposes of graphing, it's also important to remember, it's 626. We can go ahead and go over the answers. For the purposes of graphing, it's important to remember that a lot of times you want to pick a number that's going to give you what we call pretty numbers sometimes. We call them pretty numbers because they don't have a lot of decimals. They're not very large numbers. They're usually within a small range. And they give you a number that is easy to put on a graph rather than trying to go into all the smaller numbers, trying to go into the decimals, estimate all your roots. Instead of trying to do that, try to pick numbers that will give you a nice round number with a whole number with no, that's not too large or no decimals or anything. For some equations, yes, it will not be possible to have integer coordinates, like the first one in this case, which is my mistake. Don't worry about that, but in general, just a general thing to remember for the future. All right, I've got a few answers in here. Someone said for h of x, you can do 1, 6, 4, 7, and 9, 8. Let's take a look and see how that looks. The square root of 1 is 1. 1 plus 5 is 6. Yes, 1, 6 checks out. Square root of 4 is 2. 2 plus 5 is 7. 4, 7 checks out. Square root of 9 is 3. 3 plus 5 is 8. 9, 8 checks out as well. So good job to that person who submitted those three coordinates. All right, we've also got someone who put in 25, 10, 16, 9, and 9, 8. Those are all correct answers for these x and y values. And yeah, like I said, these are not the perfect example for that, but try to always keep those numbers nice and whole so they're easy to graph, especially since this was an exercise to help you get ready for graphing those radical equations. All right, now that you guys are good with that, let's move on to rational functions. So graphing, analyzing, and understanding various rational functions. We've got about 30 minutes left, and we're going to go over these last three sections. So rational function is any function which can be defined by a rational fraction, which is an algebraic fraction such that both the numerator and the denominator are polynomials. And we're going to take a look at one right here. So here in a rational function, we have 1 by x, f of x is equal to 1 by x, and f of x is equal to 1 by x squared. rational functions, one unique thing about rational functions is their asymptotes. So vertical asymptotes are easier to find than horizontal asymptotes sometimes. So to find the vertical asymptote, you want to set the denominator of q of x, or set the denominator which is q of x, to 0, and then solve for x. So if the, moving forward, if the denominator of q of x is 0, solve for x. So then first you factor p of x and q of x. So if they are completely expanded polynomials, factor them first, because that's going to make evaluating a rational function a lot easier for you. Set each factor in the denominator to 0 and solve for x. So the factor does not appear in the numerator, then it is a vertical asymptote. Otherwise, it is just a hole in the equation. We talked about that removable discontinuity, that hole in the equation last class. As for horizontal asymptotes, we got on the next slide. We compare the degree of the numerator to the degree of the denominator. So if n, which is the numerator's degree, is greater than the denominator's degree, is less than the denominator's degree, then the horizontal asymptote is just the x-axis, which is y equals to 0. If they are equal, then the horizontal asymptote is y equals to a over b. And if n is greater than m, then there's no horizontal asymptote. Rather, we will have an oblique asymptote, which we're going to be going over later, possibly not in this class. So here we have an example of that. See the vertical asymptote at x equals 3 and the removable discontinuity at x is equal to -1. So the rational function f of x is equal to 1 by x, which is the parent rational function, it can be transformed by using methods that are similar to those used to transform other types of functions. So we have the a, the absolute value of a, which is a vertical stretch, or the compression factor. If a is less than 0, it's a reflection across the x-axis. We have the k for the vertical translation, and of course h for the horizontal translation. And remember, it's the minus h, so x minus h. Very important to remember that. Now we're going to use Desmos. Desmos is an online graphing calculator that I like to use, and we're going to use that to take a look at some rational equations. Let me go ahead and switch tabs so I can share my screen again. Okay. Using Desmos to graph, and this is our Desmos graphing calculator. So these are the two equations that we're going to take a look at. F of x is equal to x plus 3 times x minus 4, and x plus 2 plus 3x. Let me change that 2 times. It's an incorrect rational function. And let's add one more factor to this. So x minus 2 to that. So we have f of x is equal to x plus 3 times x minus 4, and then x plus 2 times 3x times x minus 2. And then g of x is equal to 3 times x plus 4 times x plus 5 over x plus 3 and 8x. So since this is already in factored form, it's very easy to evaluate. We can take a look at this for taking our horizontal asymptotes. So we're going to go back, take a look at our horizontal asymptotes line. So first, find out the degrees of the numerator and the denominator. The degree of the numerator, we see there are two x values being multiplied with each other. So the degree of the numerator would be 2, and the degree of the denominator would be, we have 3 x values being multiplied against each other, multiplied with each other, so we have 3. So it's 2 on the numerator and the 3 on the denominator. So n is less than m, and in that case, the horizontal asymptote would be the x-axis. Let's take a look and see if that's correct. And we see, yes, the horizontal asymptote is the x-axis. If we make it a little smaller, if we zoom in, we can see that these values do not generally meet the x-axis. All right, we'll go on to the next one. The next one we have equal. We have an equal in both in both the numerator and the denominator. We have x squared in the top, x squared in the bottom. So go ahead and do that. Close this one down. And that one, the horizontal asymptote would be a by b. And so a by b, which is your coefficients. So the numerator's coefficient is 3. The denominator's coefficient would be 8. So 3 by 8 would be our horizontal asymptote. We can see there that's sort of where it goes. Let's zoom in a little bit more. 3 by 8 horizontal asymptote. All right, so let's go back. And now that we've gotten a look of how rational functions work, we basically have our scope of how rational functions work in general. So we're going to move on to polynomial functions. And polynomial functions is going to take a while to go over. There's a lot to go over in polynomial functions, and it's also a very, very important part of precalculus. A polynomial function is a function that involves only non-negative integer powers or only positive integer exponents of a variable in an equation. So now let's see that in action. Types of polynomial functions. So polynomial functions are generally defined by their degree or the power to which it is, and they definitely do extend way past 5, past 20, past 100. They have an infinite number of possible degrees. So we have our constant function, which is a degree 0, what we call linear function, which is a degree 1, quadratic function, which is a degree 2, cubic, which is 3, quartic 4, and quintic, which is your degree 5 equation. So take a look at this because these are all important terms that you're going to need to know when you're thinking about polynomial functions. Of course, these are not all these images right here are not all the parent functions. They're just examples. So the parent functions, these are not the parent functions of each of these equations. We can go ahead and go into Desmos and take a look at what the parent functions of these equations would be. So let's do first, f of x is equal to 0. So it's a parent function of the first one. G of x is equal to x. That's the parent function, as we know, of a linear equation, right? Y is equal to x, f of x is equal to x. H of x is equal to, let's see, x squared, which is our quadratic equation. We see that right here. Let me make it a little bit thicker. Yeah, there we go. And that's our quadratic equation we see right there. J of x is equal to x cubed. So keep in mind, remember that all these parent functions will not have any transformations on them at all. So it's just going to be that x, that one variable, and since it's a polynomial function, that one variable with a constant in the power. So we also have k of x, which is equal to x power 4. I'll go ahead and close these last two down. Right, x power 4. M of x is equal to x power 5. And see something that you notice that these two even graphs, they have even powers 2 and 4, look very similar. Let me do an n of x is equal to x power 6. And you see how similar those three graphs look. They look very, very similar. They've got that, they both slanting, they both have end behavior upwards. They both have that, they have that shape that looks a little bit like a parabola. And you'll see the same thing for all these odd functions as well. So let's take a look. P of x is equal to x power 7. And you see a similar thing there as well. They all look very, very close to each other. So that's also something to know when we're thinking about polynomial functions. So remember, take a look at this. If you want, you can go ahead and copy this into Desmos on your own time. If you've got a graphing calculator at home, you can copy that down. But this is all something that's very important to note, and it's going to become crucial to your learning of polynomial functions. Okay. Are there any questions at all so far on what we've gone over, what we've learned, anything so far on polynomial functions? Nothing at all. Okay, we can go ahead and go back. So analyzing polynomial functions, here we talk about our end behavior. So if you have an odd degree like a cubic function or a quintic function and a positive leading coefficient, then you're going to have end behavior like this. An odd degree and a negative leading coefficient, end behavior where it's x tends negative, y tends positive, as x tends positive, y tends negative, and even degree and positive, and even degree and a negative leading coefficient. So we're going to go ahead and try some of those out in Desmos. We have odd degree and positive leading coefficient. So we're going to do 3x power 3, an odd degree and a negative leading coefficient. We'll do negative 4x power 7. Even degree and positive leading coefficient, we can do 5x power 8. And we can have even degree and negative leading coefficient, negative 2x power 6. Let's go ahead and put those all into Desmos. I'm going to close out all these first. All right. So we have f of x is our first one is equal to 3x power 3. Let's zoom in a little. And we notice that our end behavior, right, as x tends negative, y tends negative, as x tends positive, y tends positive, and we see that right here. We're also going to do our g of x is equal to negative 4x power 7. Close this one down. 4x power 7, and we see it's got the same end behavior right here. And our next one's going to be h of x is equal to 5x power 8. We see both of those upward. And our last one, j of x is equal to negative 2x power, 2x power 6. And we see that both of them downward. So even when we do that, we can add as much as we want to these 4 equations and the end behaviors will still remain the same. So let me change the color of this one first to green, or to orange first. All right, and let's go ahead and change up the first one a little bit. So we're going to make it 3x power 3 plus 2x power, not 2x power 7, 2x power 2 plus 7. Turn on, and the end behavior is still the same. You've still got that same end behavior. As x tends positive, y tends positive. As x tends negative, y tends negative. And we're going to do the same thing with this other one, negative 4x plus 7 plus 6x power 6 minus 9x power 4 plus 3, or plus 2. And we've got the same end behavior. The end behavior remains the same. We're going to try once more for the last one. Let's see, 2x, or let's do it for, 2x power 6 plus 5x power 3 minus 7x plus 88. Not plus 88, let's do plus 8. Let's turn it on. And we've still got our end behavior. No matter how far we go, end behavior looks the exact same. So this is something very, very important to remember when you're analyzing those polynomial functions, and it can help you identify a function really quickly. So let's go ahead and move on. This is another chart on the end behavior of a polynomial function, but it's a little bit more organized, and it's got the end behaviors written down here as well. So if you want to take a screenshot of this, write this down in your notes, whatever you'd like to do. But this is very, very important when you're understanding these polynomial functions. I'll give you a couple minutes to go ahead and take a look at that. Moving on, this is something to note. The highest degree on a polynomial is the number of zeros or x-intercepts that polynomial has. So the highest degree on a polynomial is the number of zeros or x-intercepts that polynomial has. And the definition of the number of a multiplicity, which is what we're going to go over next, is the number of times a given polynomial has a root at a given point. That is the multiplicity of that root. So multiplicities in polynomial functions, if it's got a single zero, if p is equal to 1, 0 with multiplicity 2, or 0 with multiplicity 3. It would have that, this is called it's called a tangent. This one would go through, this is a tangent line, and this is a change in continuity. And this generally occurs with any odd value. This generally occurs with any even value, and this occurs with anything with a multiplicity 1. So we're going to take a look at this polynomial function. So already here we have our y-intercept when f of x is equal to 0. Remember we talked about our extrema last time, so our global maximum as well as a turning point, a local maximum as well as a turning point, and a double root. So see, in this equation we'd have x plus 1 whole squared. So it just touches the x-axis. This it's a tangent. This curve is tangent. We have our triple root or a cubic function. So it forms an inflection point or a change in the inflection of this graph. Curvature changes sign, and then you have an end behavior at this large x and a single root, so it just crosses the x-axis. We go back here and we remember our polynomial function. We know that the degree is even and the leading coefficient must be negative for this function because of its end behavior. So polynomial functions are always smooth graphs and they do not have discontinuities. This is another example of a polynomial function, local maximum turning point. So x equals 2 is a 0 of this polynomial function. A turning point this turning point that's just a tangent to that axis indicates an even multiplicity for that value. This turning point indicates an odd multiplicity of your y-intercept, your local maximum, and the end behavior that shows n is even and a is less than 0. All right, now that we're done with that, we can move on to inequalities. Are there any questions about polynomial functions? Let's go back. Are there any questions about polynomial functions at all? Anything that you don't understand, anything you would like me to go over before we continue on to inequalities? This is a very, very important part of learning about precalculus. Someone asked how much time do we have left? We've got about 15 minutes left. All right, I don't see any questions, which means we can continue on to inequalities, understanding, analyzing, and this would be solving nonlinear inequalities. So a nonlinear inequality is an inequality containing a nonlinear expression. So when the inequality is greater than or equal to, y is greater than or equal to a, y is greater than or equal to a or less than or equal to, in such a case, then the graph is drawn with a solid line. So while it is, if it's just greater than or less than, then it's drawn with a dotted line like we see. So here we go, we have an example of that. When y is greater than, we don't see it just greater than, we have that dotted line. Greater than or equal to, we have a solid line. And what we notice about this is we notice with our inequalities, it's all values greater than or equal to. So we have this shaded area that is above, all this shaded area is less than. And the reason it's above and not to a certain side is because we're talking about the y values here, not the x values. So it's everything above or below. So y is greater than or equal to. It's above or below. And here's another example of some solutions to these such equations. So now we're going to go over how to solve this value. So x squared minus x minus 6 is less than 0. How to solve this nonlinear inequality. I'm going to stop share for a second so I can switch tabs and we can go over to our sketch pad over here. Grid. All right. And let me write down the problem. X squared minus x minus 6 is less than 0. All right, let me go ahead and share my screen again. Okay, so this is our problem, and we're going to try and solve this problem. So what we want to do first is we want to find all the real zeros of this. Since this is a quadratic equation, what we want to do is we want to find the zeros of this. So x squared minus x, oh sorry, that's I wrote something else. X squared minus x minus 6 is equal to 0. All right, since we're just finding the real zeros of this, we can go ahead and equate that to 0. And what we're going to do is we're going to factor it really quick. We know how to factor it. We know that what adds up to -1 and multiplies out to -6, and we know that is -2 and +3. So x, and so our factors are x minus 3 and x, sorry, that would be, sorry, -3 and +2. So x minus 3, x plus 2. So these are our two factors. And we're going to go ahead and say that that means our solution would be x equal to 3 and x equal to -2, right? So now we're going to choose some test intervals over which to evaluate this. Let's pick a different color. So are some test intervals over which we're going to evaluate this. So we have, we're going to pick some intervals, -∞, comma, -2. Interval -2, comma 3, and 3, comma infinity. And so once we've evaluated that, once we put that in, we're going to come up with our last three. Let me pick a different color, pick green for this one. Our last evaluations are going to be -3, 0, and 4. And if we plug them into this equation, we're going to get now 0, comma, -6, -3, comma, 6, and 4, comma, 6. And these are going to be our final answers for solving this nonlinear inequality. So let's go back to this. And it looks like that is the end of what we have today. Does anyone have any questions on nonlinear inequalities, solving nonlinear inequalities, any of that before we do our little recap? I don't see any questions, so we can go ahead and recap. So today we learned about power and radical functions, graphing, analyzing, understanding all these functions, rational functions, polynomial functions, and nonlinear inequalities. And we learned how to graph all these types, how to understand and analyze all these types and the different end behaviors and the transformations on all these different types of functions. So before we go on to the last and go over the homework for next week, are there any questions at all about what we went over today? We will be going over we have about 10 minutes left. Oh, someone asked for this question, what are we trying to solve for? We are trying to solve for x. We want to find all values in which this equation is less than 0. Feel free to use the Q&A function or the chat function if you have any questions at all. I don't see any questions at this point. You can go ahead and ask them or raise your hand and I can allow you to speak. But since I don't see any questions, this is a homework. For the homework, you can go ahead and scan this QR code or use the link. And I want you to take some time to make sure that this works for you. It is a Google document that's going to give you 4 questions that I want you to factor, and then 2 problems to just sketch a graph for. I believe they're polynomial functions, just to sketch a graph for. So for those 2 polynomial functions, you don't need to worry about being exactly accurate. Just I want to see the functions. I want to see correct points of inflection. So let me go ahead and show you all. going to let these equations load. It's going to take a minute to load. See, these are 4 problems that you want to factor completely and then graph the following polynomial functions. All right, and it's just 6 problems total. It's nothing too hard. It's something that you should be able to do given what we learned today. We've still got a couple more minutes. We've still got about 5 more minutes. If there are any questions at all about what we went over today or how to solve the problem. Okay, I see a question in the chat. What's the difference between radical functions and polynomial functions? Polynomial functions generally will have are generally, like, we remember our polynomials. The definition of our polynomials from algebra 2, and the definition of a radical functions generally contain like a square root or a cube root or some sort of root like that. Polynomial functions do not generally contain one of those. Polynomial functions do not contain that. Yeah. All right, any questions at all? If you're taking a look at the homework and you have a question on something that you just don't understand how to do, just something conceptually you don't understand, go ahead and let me know. We have about 5 minutes left for us to go over that, and we can talk about like graphing our polynomial functions and such. Any other questions? Questions can be sent in Q&A. Questions can be sent in the chat function. All right. Someone asked in the Q&A, difference between radical functions and polynomial functions. Again, okay, we got that. Right, and someone said, can we go over graphing radical functions again? Absolutely. So let's go back. Make sure you scan this QR code or get the link. Let's go back to graphing radical functions. Let me see where it is. There we go. So this is radical functions transformations, which can also help you graph your radical functions. But graphing radicals, what we went over today is basically the simplest way that I find to graph radical functions when you're just starting out with them, which is picking a few points that will give you a clean answer. So what we went over in this one, in this our example, finding the 3 x and y values, is we found samples that would give us a whole number if we plugged it in as the x value to that equation. So some people would plug in, for the last one, they'd plug in perfect squares like 4 or 16 or 25 or such numbers like that would give you a whole number like that. So what you basically want when you're graphing these radical functions is you want a number that will give you a nice you want an x value that will give you a nice whole number when you get it out of your equation, and something that's just very easy to graph. All we're doing right now is we're not really going into really in-depth graphing radicals. It's just very simple, plugging the value in and getting a value out of it. All right, any more questions? Did I answer your question? Someone says you still don't understand factoring with exponents more than 2. All right. So the thing with factoring exponents more than 2 is that is something that it's a skill that you would have learned in Algebra 2. And we do have that on the syllabus for this course. Algebra 2 is generally something required to learn. And so in this homework, I really encourage you to go home and when you're at home, I encourage you to work through this. Think about it a little bit more. So think about you see this 9, 6, and 3. Think about those are very common factors, right? You have 4, 2, 4, 2, and then exponent of 0. So think about the similarity between the factors, between the exponents. Think about similarities between the coefficients on those values. Again, it is a very, very much necessary skill, something that you're going to need to know for almost every part of pre-calculus. And especially when we move on to trigonometric functions, you're going to be factoring with trigonometric functions. So this is something that's very, very important to remember. Yes, I'll go back to the homework. Here you go. It's just about 6:58, so I'll give you guys another 2 minutes. Any questions that you might have before the next class starts? any questions at all, here is the link. You can scan it if you want. I can paste the link in the chat. Just make sure, let me know.